My name is Alan Leibovitz, the Associate Dean and former Stats Instructor. So I do enjoy my job very much. All right, so I would have had all this set up ahead of time, and we got all this settled. All right, so what I have for you guys is one of my old exam reviews that I used to give in my class. With all the material broken down, chapter, topic, and what problem it is, let me go ahead and pass those out. I am, of course, also happy to go over any materials that you were given by your instructors. Hold on. That one's mine. So is there anything in particular you guys want to go over? Yes?
Oh, yes, I do. Testing the hypothesis.
Okay.
The null hypothesis.
Like coming up, like writing the hypotheses, left tail. Okay, first of all, who's your instructor?
Bull.
There you go.
Blue.
Okay. I only ask because with statistics, there can be some differences in technique based on the instructor. So he's heavy into the calculator, correct?
Yeah.
Okay. Just so I want to make sure I'm doing it how you're familiar with it.
Okay.
That's the only thing. So, okay, so do you have any specific questions? Do you want to go over what's on here?
I guess just the basis of it, because I don't really understand the two-tailed and the left-tailed and when it's left-tail or right-tail.
Okay. All right, let's go over in the review, starting on number 34. And I'll bring it up here for those of you watching at home. All right, so a psychologist claims that more than 8% of the population suffers from professional problems due to extreme shyness. Use P the true proportion of the population that suffers from extreme shyness. Okay, so you have to write the null and alternative hypotheses. Okay, first of all, what is being claimed? Now, well, in order to write the hypotheses, you start first with the claim, then the counterclaim, and then you label them, the null and the alternative. I have found that works best. If you just say, this is the null hypothesis, and you go from there, that can get confusing. It's actually what you want to do last. All right? So, more than 8% of the population suffers from professional problems due to shyness. Okay, so how do we write that mathematically?
Greater than 0.
Okay, so P, right, because it's the population proportion, is greater than 8%, or 0.08, okay? Remember, it's 8%. Now, in your hypotheses, one hypothesis will always have an equals, and the other will always have what I call something else. Okay? So, actually I have a question, since all of you are from the same class. Do you guys ever write less than or equal to, or greater than or equal to in your hypotheses? You will? Okay. So that's a little different than the book does it.
Yeah, he said the opposite of like one thing is less than or equal.
Okay, he does it that way. Okay. I just want to, again, I want to talk your language. In my classes, well, let's start with your classes. Well, what's the opposite of greater than?
Less than or equal.
Less than or equal to. So P is less than or equal to 0.08. Now in my classes, I would write that with just an equals. Because I have one is just equals and the other is something else based on what is done in the textbook. Based on how other people learn stats, they will write it this way. This is acceptable. Now, which one's the null hypothesis? Always.
always the equals in it.
That's the way to answer it. It's not the first one or the second one, because that can change on what you write down. The null hypothesis is always the one with the equals. So this is the null hypothesis, and that is the alternative hypothesis. Come on in, have a review. We're currently working on number 34. All right, and that would be, now on my version, notice it would be equals and greater than, so A would be the right answer. But for you guys, it would simply look like this, all right, depending on your instructor. So, is this one-tailed or is this two-tailed? That was the question you asked. Why is it one-tailed? It's very simple. It's very, very simple why it's one-tailed. Because the greater than or the less than. If it was equal or not equal, that's two-tailed. For example, okay, if we were playing a game, okay, guess a number from 1 to 100, okay, and you pick a number. 67. Wrong. Okay, you could be too high or you could be too low. That's two-tailed. Okay, if you guess 67 and I say your number is too high, that means you're only going to guess in one direction. All right, so that's one-tailed versus two-tailed. It also has to do with where the critical value, or where the regions are that you're trying to find essentially under standard normal distribution. Right, so if this is only in one direction, you're only going to include the area in one tail, because you're only going to shade in one direction. If it's not equal or not equal to, it could be in either end. So that's two-tailed. All right. Let's see. Anything else on? Do you want to do like a formal hypothesis test? You want to go through the whole thing for one of these problems? Yeah, well, we're here. That's why we're here. All right. How about number 37? In a sample of 100, number 37. In a sample of 162 children selected randomly from one town, it is found that 21 of them suffer from asthma. At the 0.05 significance level, test the claim that the proportion of all children in the town who suffer from asthma is 9%. All right, so what's the claim here?
P equals 0.09.
Okay, how do you know it's P?
Because of the last sentence.
Proportion.
Because the word proportion. I always tell my students, statistics is as much about reading comprehension as it is about mathematics. It clearly says proportion, so it's not going to be mu. All right, it's going to be P. So P is equal to 9% or 0.09. Now, I always do a little thing where I say, this is the claim. I think it makes the decision process at the end a little bit easier. So, the opposite of equal is not equal. And then which one's the null hypothesis? The one with the equals.
So, in this case, this would be one-tailed. I mean,
it's two-tailed.
Yeah.
Because we can be wrong by having it too high or too low. All right, so this is clearly a two-tailed test. All right, so if we're going to do this, again, using technology, all right, so stat, it's a test. What kind of test is it? What are we doing here?
Proportion.
How many proportions? One, right? There's just one population proportion that you're looking at. Okay? So it's a one proportion test. So that makes it, oops, too far, number 5. All right, how do we find P0? It's right here, guys. You know what that 0, this 0 stands for? That 0 really is that 0. Okay, it's the P from the hypothesis, which is 109. Now in this case, we need X and N. So going back to the problem, it's 21 out of 162.
So 21 would be your X, and 62 would be your N.
162.
Yeah, 162.
Remember, X is your sample size, or N is the size of the sample. X is the number of successes. X always has to be less than N. And then in this case, our alternative, is it not equal to, greater than, or less than, or greater than? Not equal to. How do you know it's not equal to? Because it says so right here. This is why even if you're doing a problem that just asks you something about the end of the hypothesis test, you still have to write all this down because you got to know what to put in here.
So the P naught is always going to be from the null?
Well, from the hypotheses, because this number is always going to be the same. These are never different, ever. These are always the same.
Just the sign in the middle is different.
It's the inequality, right? The potential inequality, that's correct. All right, so we calculate. And what's our p-value? 0.0, I'll call it 780, because we should do, it's a probability, we should do 3 significant figures. All right, now there's one piece of information that was in the problem that I didn't write down. What was it?
0.05.
Okay, what is that?
The confidence you have in your statistic?
Well, it's the significance level, okay, which is, what's the symbol for the significance level?
Alpha?
Alpha. All right, so then what do we do with this? What do we do with the p-value and our significance level?
Find a critical data.
All right, hold on. Do you guys use the p-value, or do you find the area of the critical region?
Find the area of the critical region.
Is that how you guys do it? Well, hey, I'm not in your class, because it can be done 2 different ways. Are you in the same class as there? Okay. So you guys find the area? Okay. Let me go back and do this. That's not how I normally do it, but that's all right.
You found it.
In this case, if we draw the picture, okay, you can see the critical region. 37. So I'm going to get rid of, well, in this case, if the significance level is 0.05, okay? So let me go ahead and draw that. What z-score gives us an area, a two-tailed area of 0.05? That's one you guys should probably know. Think confidence interval, okay? Think 95%. What's the critical value for 95% confidence interval?
1.96.
Okay, it's going to be 1.96. So our z, alpha over 2, is plus or minus 1.96. And in this case, our test statistic, Z, you may not do p-value, okay? Our test statistic Z is 1.76, all right? Which is here. All right? Here's our critical region here and here. So, is our 1.76 in the critical region?
No.
The shaded region?
No.
No. What does that mean?
It's within two-sided equation.
Okay, but what does that mean regarding the hypothesis test?
Except.
Ooh, we never accept. Never
Fail to
ever.
reject.
What is it?
Fail to reject.
Fail to reject. Fail to reject what?
The claim.
The null hypothesis.
Okay.
Can you talk about how you got the 1.76 from the p-value?
Well, you would use the formula. Okay. Now, are you guys doing this on the calculator generally? Or are you using the formula?
He told us both ways.
Yeah, he teaches it both ways and whichever way we choose.
What's the better way?
Well, I think the better way is to use p-values, but that's another story. That's my preference. So, all right, you would have to use that formula there. Hard to hide.
Proportion one population.
Right. So you'd have to plug all that into the calculator, and you would get the 1.76. But why bother? Statistics is about let the technology do all the heavy lifting, and then you come up with the right interpretation. What does it mean? All right, this isn't like when my father took statistics in 1966 when it was all tables and a slide rule, and it was ugly, ugly stuff. All right, you don't do that anymore. So you can use the formula, right? You'd have 0.09 minus P, which you get from the 21 divided by whatever. What was it? It was 21 divided by 162. And then you'd plug up, no, I'm sorry, it's the other way around. 21 over 162 minus 0.09 over the square root of 0.09 times Q, which would be 0.91 divided by 162. Who wants to do all that? It's ugly, all right? So anyway, back to this, we're going to fail to reject the null hypothesis. Now this is why I put this here. Since we are failing to reject the null hypothesis, that means we are also failing to reject the claim because they're the same thing. If the claim is here, then we have a different, we're going to have different language. All right, so since we are failing to reject the null, that means we are failing to reject the claim. Why are we failing to reject it?
Because it's an accepted value we got. It was inside the curve.
True, true.
Within one standard.
But why, if we were to reject it, why would we reject it?
Because it'd be outside the end of the tails. The value.
Okay, but what I'm after here is how do we come up with the language of the hypothesis test here? Okay? And if we reject an idea in life, in society, whatever, it's because we have evidence to say that that's wrong. So if we reject the null hypothesis, why? Because there's evidence to say so. So if we won't reject an idea, now we're not accepting it now, we're failing to reject it. When will we not reject an idea? When we don't have enough evidence, all right, to say otherwise. So in this case, we say there is not sufficient evidence to reject, right? Because that's what we're not doing, we're not rejecting. to reject the claim that, and I'm going to shorten this here, you always use the language of the problem. So there is not enough evidence to reject the claim that
Proportion of all children is found who suffer from asthma is 9%.
that the proportion of all children who suffer from asthma is 9%. Come on up. Here's going to read you up. You're welcome. Are you from the same classes then? Who?
Cool.
It's for stats?
Oh, yeah.
Okay. Now another way to do this is to say if the p-value, right, a lot of this is based on things being unusual, right? You've done the rare event rule. The rare event rule, right? When things are unusual, you reject the claim. Right? You talked about that earlier in the course. So if the probability is less than alpha, the p-value is less than alpha, that means you have a rare event, an unusual event, and the assumption, which is the null hypothesis, is wrong, and you reject it. Right? It's a different way of thinking about the same thing. Did that answer your questions? Did it confuse you?
I mean,
What's
it's
the
so hard
question?
to take in, you know.
It is, but you got to work through the procedure. Now the thing about stats, and in this course in particular, even though chapters 8 and 9 look very different, they're really the same thing. It's whether it's a mean versus a proportion, but you're doing the same procedure, right? What's your claim? What's your counterclaim, right, or your opposite claim? Plug everything into the calculator. What's your critical value? Or excuse me, your test statistic compared to your critical value or values. And then, do you reject or fail to reject the null? And then what's your conclusion? It's the same procedure over and over again. Okay, question on that one?
Chapter is this one. Chapter
This is, if you look on the front of your packet, it's got the list there.
Right.
This is, all hypothesis testing is basically chapter 8. There's a little bit in chapter 9.
Okay.
Yes. When you did the other calculator, that's your z-score, right?
Yes. That's the test statistic. All right, that the one that comes up.
Oh, we could just do it that way, yeah. Instead of doing that formula thing, it's...
That's what I said.
Oh, okay.
All right, so there is your test statistic. All right, the Z.
Oh, it gives you the p-value and the z-score.
Yes. So what the p-value is, just so you know, it's finding, because this is a two-tailed test, it could go left or right, plus or minus. It's really finding the area to the right of this Z and to the left of the opposite Z.
Why is that a two-tail again?
We talked about that. What's the difference between this one and this one?
Oh, the sign. Okay, I remember.
So why is this two tails?
Because of the equal sign?
Well, they both have an equal. It's the inequality that's important.
If it has greater
Okay.
than or less than, it's one tail. Because you can only go...
Remember, pick a number from 1 to 100, and you pick 67, and I said wrong. So that means you could be too high or too low. So that's equal or not equal. Okay? But if it's a less than or greater than, then it's one tailed. All right. Any other type of problem you guys want to go over? Hypothesis test, confidence intervals, probabilities, tables, correlation, regression. If you guys again want to look at the front of the packet, it's got a list of things: binomial probabilities, normal distributions, central limit theorem.
Yeah, the central limit.
Okay, central limit theorem.
We'll actually start from the normal distribution. It's a central.
Okay, so starting 21 through 25 here. All right. Did you guys do the normal PDF and normal CDF functions on the calculator?
Yes.
Okay.
Don't remember.
Okay. All right, 21 is one of my favorite questions. That's actually one that I came up with. The mean height of women is 63.6 inches with a standard deviation of 2.5 inches. Which height would be considered unusual?
Something that, all right, 2 times 5 inches, something greater than 68.6.
All right.
Something outside of that.
Okay, you're very fast, but yes, okay? So remember that on the standard normal, or on normal distribution, if you have the mean in the middle, then the range of usual values is the mean minus 2 standard deviations to the mean plus 2 standard deviations. Anything outside of that would be considered unusual. So this is 63.6, and this is 63.6 minus, oops, 63.6 minus 2 times 2.5, and 63.6 plus 2 times 2.5. Well, 2 times 2.5 is 5, so this is going to be 68.6. and 58.6. So which of those values would be considered unusual? 58. All right, 58 is outside this range, just barely. Okay? You could also do z-scores for this if you wanted to, but that's basically what we're doing here. All right, so for 22, you're given something with a mean of 60 and a standard deviation of 4. Find the probability that your random variable x is less than 53. So I always suggest draw the picture. You've got to see the picture on this, even if you are using the calculator. So in this case, the mean is 60, and here is 53, and we want to know the probability of getting something less than that. Now in your class, do you guys convert this x to a z-score first, or do you go ahead and use the 53? Okay, but I'll do it 2 ways. So whenever we're finding a region under the normal curve to find the area, which is what the probability is, it's going to be the normal CDF from left to right. So what's all the way to the left here? Close.
Minus e to the minus.
Okay, it's negative infinity, but it's infinite, and I'll get to that in a second. Comma 53, followed by the mean, which is 60, and the standard deviation, which is 4. So again, the syntax here is normal CDF, left to right, followed by the mean, followed by the standard deviation.
Being it's a multiple choice test, before we get into like the meat of the problem, you could probably just look at the answers and try to understand what it's asking for. And there really is only one choice here. For understanding what you're looking for.
Not at all.
No? Okay.
A and C are reasonable answers.
Oh, that's right. I thought that was 40%.
Well, it could still be 40%, but all you know is it's less than half, right?
Much less.
It depends on the standard deviation, right? You ever see, pictures not necessarily drawn to scale, so don't trust that. Question?
Yeah, what was the L and R? Is that?
Left to right. So left bound to the right bound. So all the way to the left. Where does this end going to the left? It doesn't, so it goes to negative infinity. Now there are two ways to type in the negative infinity, and you can see one here, okay? The negative E99. So whenever you see the negative 1 E99, that's basically negative 1 times 10 to the 99th power. That's as big of a number as you can enter.
That's a normal CDF, right?
Yes.
It looks different.
He's got the good calculator.
Yeah.
Yours should have been updated at the LRC. It hasn't been? Okay, you're going to type it in like this. It's going to be the same thing. We're going to type them in the same order, but you're going to put commas in between them.
Is there a way to update this?
You can download the software, the new operating system. Is that an LRC calculator or is that yours?
Fine.
If you do a search online for update TI-84 operating system, you can do it very easily and it's free.
Can the 83 get the update too?
Not all of them, no. But it's, trust me when I tell you, I'm writing it this way. This is how you're going to type it into the calculator. Now, another way to think of this negative infinity is a negative, describe infinity in one word.
Continuous line.
How about big? How about really big? So what I like to do is, just to keep, because I don't like this whole scientific notation E format, I just do this. It's negative. Okay. Really big number. I just hit 9 like 8 times. All right. It does the same thing. All right. And then what's the upper bound?
53.
Right, based on the picture, 53. Followed by the mean, which is 60. And the standard deviation is 4. But you're going to type it in. So you can. This is what it looks like on your calculator. You can tell this is what I'm used to. I haven't taught a class yet with the updated operating system. This is what I'm used to teaching. All right, you guys got it?
Yeah.
Before I hit paste? Then it's going to put it in the format like your calculators. And then it gives you an answer. Now, is that what you guys are used to in class? Okay.
So are you looking at stuff
Yeah, the negative 1 or the positive 1, E99, is fine. No sweat. You should get the same answer. All right, so it's 0.0401 when you round. Okay? Someone has a score. All right, 23. Scores on a test are normally distributed with a mean of 69.4 and a standard deviation of 10. Find the test score representing the 81st percentile. Now, how is this different from the one we just did?
You won't have a standard deviation. What we do?
You're looking for a specific point.
As opposed to this one, we were looking for
The general area.
the probability or the area. All right, in this case, we were given the x of 53, and we get to find the area or the probability corresponding to that. This is just the opposite. We're given the area, which is the bottom 81%, and we're asked to find the test score. So we're finding the X value. So we're doing this backwards. So how do we do that on the calculator? No?
Inverse.
Inverse norm. When we do things backwards in math, what's the opposite of addition? Subtraction. What's the opposite of multiplication? Division. What do we call those pairs of operations? Inverse operations. So instead of doing the normal CDF, you're doing the inverse norm. You're doing it backwards. So for the inverse norm, it's always going to be area to the left, and that's important. It's got to be to the left, followed by the mean, followed by the standard deviation. So in this case, we have a mean of 69.4. And the 81st percentile. Well, is the 81st percentile, is that more than the mean or less than the mean?
54.
It would be more.
It's going to be more. So it's going to be somewhere here, whatever this is. All right, so how much area is in this right tail? It's in the problem. 19%. Or 0.19. So how much area is in the left tail?
181.
81% or 0.81. So in this case, it's going to be on the calculator. So stat over there. Oops, I'm sorry, distribution. And the inverse norm is number 3. So in this case, what's the area to the left? 0.81. Make sure it's 0.81, can't be 81. Followed by the mean, which in this case was 69.4, followed by the standard deviation of, not standard deviation from the problem, what was the standard deviation? It was 10. There you can see it on the calculator, right? That was a little bit more like what you guys are typing in. And we get 78.2. Okay. All right, 24 has to do with the central limit theorem, coming back to your original question. So 24, the weights of fish in a certain lake are normally distributed with a mean of 14 pounds and a standard deviation of 12 pounds. If 16 fish are randomly selected, what is the probability that the mean weight will be between 11.6 and 17.6 pounds? Now, how do you know this is a central limit theorem problem?
Because it's giving you, it's asking you to find a number within 2.
No. You can do that for one of these problems, could have been between 2. The difference between this problem that we did, we were given one value here of 53. Whereas this one, we're talking about a random sample of 16 fish. It's that sample size that makes it a central limit theorem problem. It's the N. It's not the left bound and right bound being finite. All right? It's always a group of size N. That's a central limit theorem problem. Either way, we're going to do the problem the same way. So go ahead and draw the picture. So we have a mean of 14 in the middle, and we want to know what's the probability that the mean weight of these 16 fish will be between 11.6 and 17.6. You always want to shade in your region. So it's still going to be a normal CDF. And what's the left bound of our shaded region? 11.6. What's the right bound of the shaded region? 17.6. What's the mean in this problem? 14. All right. Now notice we haven't done anything related to the central limit theorem yet. Not a thing. Now, in the central limit theorem, what changes? In the application of the central limit theorem, well, the n makes it a central limit theorem problem. But what does that actually do to a problem? What do we have to account for when we're taking in that sample size with the central limit theorem? Right here. That we know the mean of the sample means is the same as the population mean. All right? The central limit theorem says that doesn't change. What does change is the standard deviation of the sample means is now the original standard deviation divided by the square root of n. Right? That's how the standard deviation changes. You actually get a narrower bell curve. So here, instead of putting just sigma, I'm going to put sigma over the square root of n. It's the only difference. All right, so sigma, the standard deviation is 12, divided by the square root of n, which is 16. Right? Standard deviation of 12 says right in the problem. So when you're typing this into the calculator, so it's still a normal CDF. Our lower bound is 11.6. Our upper bound is 17.6. The mean is 14. And the standard deviation. Now, should you be so bold and you actually want to do a little bit of arithmetic in your head, the square root of 16 is 4, and then 12 divided by 4 is, you can just type in 3. But what if this was, 91 divided by the square root of 816? All you're going to do is type this in. So it's 12 divided by the square root of 16. That's it. Make sure you remember to divide. It's a very common mistake. Students forget the division. And there's the answer.
Why aren't these formulas put onto the sheets? There's so many of them in the calculator. It would make it so much easier for us.
There is a limit with the formulas with how much we're willing to give students because you do have the technology. And it varies by instructor. Some instructors give more, some give less. Like I don't give in my classes the pages that have how to write the answers to the hypothesis test. I don't give that to my students on the test. They have to know that. So it does vary. All right, let's talk about number 25. Number 25 is a statistical thinking question. A study of the amount of time it takes a mechanic to rebuild the transmission for a 1992 Chevy Cavalier shows that the mean is 8.4 hours and the standard deviation is 2.1 hours. The results from the study showed that the times were normally distributed. 25 randomly selected mechanics take a course on how to rebuild a transmission more efficiently. After completing the course, the 25 mechanics have a rebuild time of 7.9 hours. The probability of 25 mechanics have a mean rebuild time of 7.9 hours or less is 0.117. Based on these results, can we say the course is effective in reducing the time required to rebuild transmissions? Now, if there's one question I want students to be able to answer on my exam, it's this question. Because this is all about statistical thinking. All right, so let's look at the options. No, because the sample size is not big enough. Yes, because it is unusual to get a mean time of less than 7.9 hours. No, because it is not an unusual, it is not unusual to get a mean time of less than 7.9 hours. And yes, because the mean time is decreased by half an hour. So what do you guys think? Come on, let's just talk about it. What do you think?
Is it possible to answer without doing the work?
Absolutely. All the information you need is written in the problem. In fact, I gave you guys the probability. Well, let's look at the options. Let's look at choice A. No, because the sample size is not big enough. What do you think about that answer? Is the sample size big enough?
Yeah, it's less than 30, right?
It is less than 30, but the central limit theorem states if the original sample comes from a normally distributed population, then the size of the sample does not matter. You can have any sample size and you'll still have a normal distribution. And then the problem, the results from the study showed that the times were normally distributed. So we have a normally distributed population already, so we don't need a sample size greater than 30. So this one is out. Okay? Let's look at choice B. Yes, because it is unusual to get a mean time of less than 7.9 hours. Well, is that an unusual event? What was the probability of getting a rebuild time of less than 7.9 hours? 0.117. Is that an unusual probability? Why not?
Because it's greater than 0.05.
Because it's not less than 0.05. Right? Remember, if a probability is less than 0.05, then we say the outcome is unusual. This is not less than 0.05, so it's not unusual. So that means B is wrong. C could be right. What about D? Yes, because the mean time is decreased by 0.5 hours. What about that? All right, I have a saying in my classes. When answering a statistics question in a statistics class, your answer should involve statistics. Where's the statistics here? Another thing I tell my students, if it's an answer you would have given before you took the class, it's probably wrong. But this is how people would think. Right? Oh yes, clearly it went down. But did it go down by any statistical significant measure? That's what you learn in this class, right? You could have subtracted 8.4 minus 7.9 and say, yes, it got smaller. That's all you needed. What did you need the class for? Right? This is a non-statistical answer. This is for people that don't want to do any of the work. And just, oh yeah, it went down. Okay, this is a nonsense gobbledygook answer in statistics. This is there to get you if you're not paying attention. The correct answer there is C.
And the reason why that's the correct answer, not taking into account that you disputed all the other ones, but because it is not, because 7.9, it's still within the normal range, right?
Yeah, or it's not in the unusual range, yes. It's not beyond 2 standard deviations from the mean. If you want to, if that's the approach that your instructor takes, and it seems like he does, you guys have mentioned that a couple of times, then yes, it is not outside the 2 standard deviations of the mean range.
So how would you do this one on the calculator?
There's nothing to do on the
Nothing to do,
calculator.
you just have to
That-
reason it
the only
out.
thing to do is to get this probability, and I've already done it for you.
Okay.
The question is, can you interpret the answer? Do you know what this means? Can you apply this? Can you tell your boss, you know what, this course they took really doesn't do any good. It's not worth the money. Right? Can you apply this in the real world? Can you make a decision? That's what this question's about.
Okay.
All right. What other topics do you guys want to go over?
Possibly the frequency distribution,
Okay?
because my teacher has one on one of the tests that we did previously. And I don't know if it's on here, but can I give you what he wrote? Because I got really confused on it.
Yeah, sure.
Okay.
All right, go ahead and pass that forward, please. Go ahead and pass it forward.
Oh yeah, hold on, let me find that. Okay, it's for the width.
Which number?
Oh, the class
It's
width?
number 2, yeah.
Okay.
I wrote on it, I'm sorry.
That's okay.
He got like 5, and I don't know how he got that answer on the.
Okay.
Is it in here?
Okay. First of all, there's an issue with this particular problem because the width is not consistent. All right, that's really the issue. All right, width is defined. First of all, how do you, if I say, put your hands out, okay? If I say, show me width, what are you gonna do? You would think this, but in statistics, that's wrong. Width is measured this way, from one class to the next, okay? So let's look at this in particular, okay? Well, we'll look at this particular problem, just to talk about width. The definition of width is the difference of any 2 consecutive numbers of the same type from adjacent classes. So in this case, you can take the lower bound or the upper bound from 2 consecutive classes and subtract. So 70 minus 60 is 10. 80 minus 70 is 10. 90 minus 80 is 10, and so on. Here we have, say, 81 minus 70 is 11. 92 minus 81 is 11. Now the problem that you were given here is if you use either the left, you get a certain set of answers, which is what you did. But on the right, there's a problem, okay? I would say if you were to do it from, based on, I can see his definition, do it from the right. So if you subtract the upper bounds, you'll get the width. So in this case, it's 94 minus 99 is 5. Go ahead and look at it. See, you subtracted on the left, you subtracted the lower bounds, but if you subtract the upper bounds, I think you'll get the answers that he's looking for. Do you understand?
So am I not supposed to do the other ones?
Based on how that's graded, I would say no. I would say stick to the lower bounds, or excuse me, the upper bounds. The the ones on the right.
So, would it be best to just do the lower bound and the upper bound?
It depends. See, when I give a problem, there's always consistency. It's always going to be the same width in each one. And that problem that she's talking about, the width is different in each class. So where you subtract makes a difference.
I was more confused on how we got the last answer though, because I only got the top 4.
Well, okay. So what's the last class? Read it to me.
Read the last class. It's 83 to 94, then 95
Well,
to
83 to 94, and then
95 to 99.
okay.
What?
So when you subtract,
Those, it's 5, yeah, but
so that's okay. Here's another way to do it. Okay, you ready? Let's count. Now you can do this with integers. If you have decimals, it gets tricky. Okay, but let's count. 95, 96, 97, 98, 99 is a width of 5. That's it. That will always work. I don't think it's the best way, but when you have one, let's say, what's the one above it? Above this one?
76 to 82.
76 to 82. Notice how inconsistent these are. They're not the same width. So I would say, okay, 76, 77, 78, 79, 80, 81, 82. That's a width of 7. This one, 83 to 94, 83, 84, 85, 86,
So
87,
the
88,
width is
89,
just
90, 91,
that
92,
line,
93,
it's
94.
not from the one above it to the one under it.
Well, it's how many values, essentially. It's the width of that class. The way to do it is to subtract. But if you subtract these, you're going to get the wrong answer. If you do 99 minus 95, you're going to get 4. It's not, it's 5.
So you're basically counting the line?
You can do it that way. Now, if there's decimals, then it becomes a lot trickier. All right? Which is why generally I don't give ones where the width is different in each class. It's the same. All right? Do you guys want to go through this one? How to construct a frequency table? Okay. So you know you've got a lower class limit of 60 and a width of 10. All right? So knowing that the width is 10, and you're starting with 60. What's the next number you should write down? 70. And where does it go? Say it again.
Below 60.
The next class.
Okay.
That's where that width of 10 is. See, if you think of width this way,
Put it up.
you're going to put it here and then it's wrong. That's the problem. So since this one starts at 70, where does the previous class end? 69. Right, to 79. So this will be 80 to 89, 90 to 99. So then the other thing you have to do is you have to take these values and basically put them where they belong. Now the way I usually tell students to do this is by tick marks. All right, as opposed to trying to count up all the ones from 60 to 69. So if I've got a 98, a 72, a 71, a 64, 2 71s, a 98, an 84, and so on, I'm not going to do the whole thing, you'll eventually get the count of how many. Well, we know that these two are wrong, right, because the width is wrong, right, the classes are wrong. So we know it's one of these two. So I'm not sure what the right answer is off the top of my head. What is it? It's D, okay? So this one is just brute force. You just got to go through and you got to count them all. That's it. Okay? Now number 4, construct a relative frequency distribution. Now, what I did when I wrote this problem, I actually combined 2 different types of tables to get some wrong answers. Now, what was another type of frequency distribution? Did you guys do relative frequency distribution with the percentages?
Sounds familiar.
Okay. Did you do cumulative frequency distributions? All right. I combine those two things. Relative means percentage. Adding up to a total or to a maximum is cumulative. So what I was really asking students, my wrong answers here was not wrong data. Like the previous question, I had just incorrect numbers. This one, I took a different type of table and I mixed and matched them together. And I want to know, do students know what a relative frequency distribution is supposed to look like? Well, which one is what a relative frequency distribution is supposed to look like?
A and B.
A, what's wrong with B? The percentages are right. But these scores, these cumulative score totals, right? Less than 61, less than 71, less than 81, that's what you would see on a cumulative frequency distribution. All right? This one would be the cumulative frequency distribution, right here. And then these two are a mix and match of those two. Okay? Any other types of questions regarding tables or graphs or? All right, you guys have one more? Anything else? We got a few more minutes. Any type of problem you want to go over?
How about number 12?
Number 12, it's just a probability question. All right, the table below describes the smoking habits of a group of asthma sufferers. So you've got men, women, and whether they smoke or not and how much. If one of the 529 people is randomly selected, find the probability that the person is a man or a heavy smoker. Now there are a couple of different ways to do this. You can use the formula. Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So in this case, what is the probability of getting a man or a heavy smoker? I'll abbreviate there. Is the probability of a man plus the probability of a heavy smoker minus the probability of both a man and a heavy smoker. Now the reason why you have to subtract is when you're counting up all the men, there's 525. When you're counting up the heavy smokers, it's 31. But you've double counted the intersection of 8 of them. That's why you have to subtract it off. So this is going to be the probability of getting a man is 225 out of 529. Plus the probability of getting a heavy smoker is 31 out of 529. Again, 529 is the total you can see here. Minus the intersection is 8 out of 529. Now, since you have a common denominator there, I'm just going to add or subtract the numerators. So 225 plus 31 minus 8 is 248 divided by 529 is 0.4688 is probably what I have for the answer. Now, I think an easier way to do this is basically to count the appropriate numbers or the appropriate cells if you think of this as a table. So we want men or heavy smokers. That would be this, 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 and that. right? Are those all of the people, the counts of people that are either men or heavy smokers? What do you guys, yeah? Well,
Why is
it's,
it 23?
what?
Why is it 23 simply?
Because those are the heavy smokers. Remember, it's men or heavy smokers. Now, I could add up these numbers here, but I already have that total. Is 225 plus 23. So 225 plus 23 is the same 248 that we got before. So I am not a formula guy when it comes to this type of problem. I say count them up. What's your subtotal divided by your total? And we get the same 248 as we got before, and the total is still out of 529. So you divide, you're going to get the same answer. All right, I want to thank you guys for coming.